Now we move from ZKP theory into developer practice. You'll see how frameworks and SDKs turn circuits, schemas, wallets, APIs, and verifiers into real application flows, and how to evaluate their performance, scalability, and trade-offs. At this point, the full path is in view. Identity foundations, verifiable credentials, DIDs, cryptographic signatures, zero-knowledge concepts, and issuer-holder verifier flows. Topic 4.1 introduced selective disclosure. Next, we make those ideas practical by looking at developer-friendly ZKP frameworks and SDKs for web applications. The tooling ecosystem sits on a spectrum. At the top, identity SDKs and wallets help with issuing, storing, presenting, and verifying credentials. Deeper down, ZKP frameworks expose circuits, keys, proof generation, and verifier APIs. The goal is to match the layer to the problem, not just choose the strongest cryptography. Consider credential format, DID support, language stack, interoperability, privacy needs, documentation, maturity, and operating cost. These tools offer different entry points into privacy-preserving identity. VC and DID SDKs manage credentials, identifiers, schemas, and exchange flows. Selective disclosure libraries reveal only what a verifier needs, such as proving someone is over 18 without exposing their birth date. ZKP frameworks work at a lower level, defining statements, compiling circuits, generating proofs, and verifying them. Protocol-specific SDKs package opinionated flows for areas like compliance, access, or reputation, often trading flexibility for speed. In practice, engineers usually combine VC tooling and ZKP tooling. AVC SDK handles credential formats, DID resolution, issuance, storage, and presentation verification. A ZKP framework handles circuits, constraints, proof generation, and verifier code. The wallet becomes the integration point. It holds credentials, applies disclosure rules, and may request a proof when privacy requires more than showing a signed claim. Language and platform support often determine what is realistic to build. A useful way to think about ZKP tooling is manual versus automatic transmission. Low-level circuit coding gives maximum control, but the team must understand constraints, circuits, and cryptographic pitfalls. Middleware and protocol SDKs can deliver common flows, such as access control or KYC, much faster. High-level identity SDKs may let you express checks like age over 18, but they can limit formats and predicates. Choose based on customization, interoperability, audit needs, and delivery speed. Before a zero-knowledge proof can exist, you must define the exact truth condition being proven. For example, this credential is valid and the holder is at least 18. Some inputs are public, such as the issuer, challenge, and policy. Others remain private, such as birth date, secret keys, or hidden claims. The framework turns that mix into a proof the verifier can check without learning the private values behind the result. Most ZKP frameworks express that truth condition as a circuit, the exact logic that must hold. Private inputs, like a credential or secret value, are combined with public inputs, like an issuer key or threshold. Constraints capture the rules. Age is at least 18, a hash matches, or a signature verifies. A domain-specific language makes those rules writable by developers, then compiles them into proof generation and verification. Higher-level predicate APIs let you describe what must be true without building the cryptographic machinery directly. You might request proof that someone is over 18, in an allowed region, a valid member, or holding a credential from an approved issuer. The SDK can assemble the proof request and verification flow. Still, abstraction is not magic. Check predicate semantics, credential formats, issuer trust rules, revocation behavior, and challenge handling. Then version and test those policies like authorization code. In a typical application flow, the verifier sends a proof request, what claims are needed, which issuers are trusted, and a fresh nonce to prevent replay. The holder reviews the request and approves only the disclosure they accept. Then the wallet, app, or local agent selects matching credentials and generates the proof privately. The verifier receives the presentation proof, checks it cryptographically, and makes the business decision without seeing unnecessary raw credential data. Verification should be treated like token validation, but with more gates. The backend receives a presentation and checks the cryptographic proof. It then confirms the issuer is trusted through DID resolution, registries, or governance rules. Next come operational checks: expiration, revocation, nonce, audience, and replay protection. Only after the schema and business policy match should the system make a decision, such as granting access, approving a discount, or passing a compliance check. One practical pattern is privacy-preserving access control. The verifier sets a policy, such as trusted issuer and age over 18. The holder creates a zero-knowledge proof that satisfies the policy without revealing their birth date or other credential details. The backend verifies the proof, then issues a short-lived session or access decision. Store only what you need. Performance in zero-knowledge systems is a system trade-off, not a single benchmark. Proving is usually the expensive side, especially on phones and browsers where CPU, memory, and battery are limited. Verification is faster, but it still adds latency to protected API calls. Proof size affects payload limits, bandwidth, and storage. Key material or setup artifacts can also shape deployment pipelines. Before choosing a framework, model the full path: client capability, server throughput, network cost, and operational complexity. Production ZKP systems require operational discipline, not just sound cryptography. Cache public static artifacts like verification keys, schemas, issuer metadata, and DID documents, but never private user data. If proof generation takes time, move it into background flows so the user experience stays responsive. Where safe, batch verification or pre-compute reusable pieces. Then monitor what actually breaks: latency, payload size, wallet versions, policy mismatches, and verification failures. One rule remains non-negotiable: preserve nonce freshness. You now have the practical map. Choose tooling at the right layer, define proofs through circuits, schemas, predicates, and policies. Then connect proof generation with holders and verification with services. In production, balance speed, cost, usability, and security. Next, we turn this into stronger threat models and best practices.